Now we have talked about the basics, immersions. Now we talk about really the target, the applications. Eventually, all the remote sensing has to be applied. If there's no application, no value. So here, as we have spent lots of time talking about remote sensing reflections at IOPs, they are really tightly linked. Okay, we can use remote sensing reflection spectrum to invert various IOPs. Then, okay, the question is, so what? You can have tons of these IOP products. So what? What can you do with that? That's where our focus today. But historically, it has been chlorophyll. I guess you must have noticed that already. Everything, from synthesis to models to virus to biogeochemical models, is chlorophyll, right? Everything chlorophyll. As we talked about, actually, if we want a chlorophyll from IOPs, we can also give you chlorophyll. And we may give you a better chlorophyll. Remote sensing reflectance is a function A and BB. We show that from A, we can get this APH spectrum. From APH spectrum, which include the chlorophyll A concentration, the contribution of chlorophyll concentration. So from this, we can also get you chlorophyll. Remember yesterday we talked about the normalized specific absorption coefficient of chlorophyll? So you use this to divide that normalized absorption coefficient. Then you get chlorophyll A concentration. Actually, those are built into the CADR, GSM, and the GLP. Basically, those chlorophylls in CADR algorithm, in GS algorithm, in GLP algorithm, it's a conversion of this APH to chlorophyll A concentration. So in IOPs, we can also get you the chlorophyll. Sometimes it's explicit, sometimes it's embedded. Like in CADR or GLP, it's embedded in it. What really derived in those algorithms are actually the IOPs, the absorption coefficient. Then it's kind of described or kind of in a way to show that how we are not deriving IOPs, we are deriving chlorophyll. But in essence, what derived is IOPs. But then from the APH lambda, then get to the chlorophyll A concentration. Then you want to say, okay, here's a little bit kind of a background. Why chlorophyll? Why just we are dying for chlorophyll? Fundamentally, it's trying to use that for the primary production. In the early days, back to the Dark Age, okay, Stone Age, we just everything using chlorophyll to estimate the primary production. This can trace back all the way to the 1950s, 1930s. Especially after 1960, after China Yanchi invented that instrument or approach, can quickly measure chlorophyll concentration using fluorescence. Then bingo, since everything, as long as we can measure chlorophyll, then we can get primary production. Especially then we get to this ocean color emissions. The primary goal is to get a primary production in the basin scale of the global oceans. And for that, the central target is chlorophyll concentration, because in the early days, all the primary production model is based on chlorophyll concentration. That's why I want chlorophyll. Then you look at the photosynthesis. Okay, primary production, what is that? What is primary production? It's an estimation of the photosynthesis. It's a quantification of photosynthesis. What is photosynthesis? I bet you know better than I do. It's you have CO2, H2O, phytoplankton, get light, nutrient, convert to chemical energy. Okay, so in this system, light and phytoplankton are two of the things we can get or estimate from ocean color remote sensing or from satellite remote sensing. Satellite remote sensing gives us light at the surface, even light at the depth. Satellite remote sensing can get us phytoplankton. But then, because in the early days, primary productivity, their model is based on chlorophyll concentration. So this phytoplankton is represented using chlorophyll concentration. That's why we want that. But you look at bigger picture about photosynthesis, okay? You get, at the surface, you get the light, then at some depths, the irradiance get to depth and irradiance. For photosynthesis, we need the biomass profile. Basically, we need the phytoplankton profile. We also need a photosynthesis light model. Basically, need, if we have 100 photons absorbed by phytoplankton, how many of that will be converted to chemical energy? That photosynthesis. So actually, what we really need is phytoplankton and the photosynthesis parameters. Historically, this phytoplankton is represented or used using chlorophyll concentration. Basically, it's an index. We need some kind of index to represent phytoplankton. Photosynthesis parameter is something beyond remote sensing. Okay, so it's based on models. You have to base on laboratory measurements. After you know this, you can get a primary production at the depth. And historically, for this phytoplankton, you can use any index for phytoplankton, but historically it's used is chlorophyll A concentration. So that's how, in the past many decades, ocean color remote sensing is chlorophyll centered. Everything chlorophyll. From ocean color spectrum, that remote sense reflectance, we get a chlorophyll. Chlorophyll, then we can estimate KD, that diffuse attenuation coefficient. Then from chlorophyll, we get a primary production. So that's a system. This system is chlorophyll central. After the chlorophyll systems, everything is solved. But this thing only works for IOPs covariate with chlorophyll. Remember just a moment ago I taught you, when we use remote sense reflection, do a ratio. That ratio do not give us chlorophyll. The ratio to the first order give us IOPs. Then we put some fudge factor there to convert that IOPs to chlorophyll. Then we call it chlorophyll. But first order thing is still, actually it's IOPs. So actually there's another system. We call it IOP-centered system. From ocean color, remote sense reflex spectrum, I get IOPs. These IOPs include A, BB, APH, as I just discussed with you guys moments ago. From these, we can get a KD, and we can get primary production after we know those auxiliary information, such as photosynthesis parameters, such as light at different depths. If we have information nutrient, then we'll do a better job. So from IOPs, we can do all the things what supposed chlorophyll did. And this can do better because in this system, we do not make assumptions about the covariance among different components. We do not make an assumption about, say, CDOM has to covariate with chlorophyll, or particles have covariate with chlorophyll. Those are independent properties. So I'm going to show you a bunch of examples for these applications. That's what we are going to cover in this session. The first application, if you check the MODIS standard product, it has a diffuse attenuation coefficient at 490. That's a heritage product started from CZCS, has really about 3 or 4 decades of history. How that is estimated, basically that KD 490 is also estimated from the ratio of RS and lambda 1, basically blue to green ratio, okay? All KD can be estimated from the chlorophyll. That's Morel system. You know the chlorophyll, you put in that empirical relationship, then you can also get KD at different wavelengths. Then let's take a further look on this simple ratio derived KD. In the NASA system, KD 490, it's A1 plus A2 times this is the ratio. These are empirical coefficients, or B1, P2. These are empirical coefficients. These are early algorithms. Later on, this has been derived this way. KD 490 is KD bio, it's that formula plus this constant. Okay, that's the standard algorithm used for NASA to get KD 490 for MODIS, C-waves, or VIRS. Do you guys know what KD 490 is? Okay, it's basically the diffuse attenuation coefficient of the downwelling irradiance. I think Kurt has shared with you what's downwelling irradiance. Downwelling irradiance at the surface, then at 5 meters, 10 meters, all the way down. So there's an attenuation coefficient for that irradiance. That attenuation is called this KD. Okay, 490 means at 490 nanometer. Okay, then we have this KD 490 as a standard product estimated by this algorithm for the NASA standard product. At the same time, this standard product for curve A by NASA is the same ratio. Basically, it's a blue to green, but blue, basically it's a peak between the 443 and the 486. For the KD 490, that's a 486 divided by 555. Green is 555. So what this says, for coastal waters, we are using the same ratio deriving two products. And kind of implicitly, we are assuming these are two independent products. One is curve A, one is KD 490, right? This kind of sounds like two independent products. But we are using the same ratios. That's showing for these yellow colors. These yellow colors is the same ratios used to derive KD 490 and the curve A concentration. Does that make sense? No. You think about that. One ratio can only give you one product, right? Mathematically and physically. There's only one freedom. How can this one ratio give you two or three independent products? That's one argument. Another argument, look at it. These are so-called coastal waters. Coastal water generally will indicate that optical properties do not covary well with chlorophyll. But here, when you use the same ratio to derive chlorophyll and KD, that means the two products are completely covariant. So that means these two products, at least in the spatial distribution, it's exactly the same. There's no independent information, spatial information. Although the two values will be different because KD has different values, chlorophyll has different values. But spatially, it's exactly the same. No extra information provided by this kind of product. For the open ocean, chlorophyll uses 443 divided by 555, and KD 490 uses 486 divided by 555. Yes, seems to use two different ratios. But for open ocean, 443 and 486, it covaries. Because open ocean, it has to covary because open ocean, there are not that many constituents to change the light field. Pretty much the phytoplankton dominate these variables, these independent constituents. So in the open ocean, generally 486 and 443 covary very well, as shown here is 0.99. So even for the open ocean, although we use the two different ratios to derive the two different products, but they're still highly, highly covariant. What does that say? That says, again, these two products have no actual information by another product, instead of just giving you a different number, different value. So that's something actually just unfortunate, because historically has been that approach. Simply we like to use ratios to do regressions, then we try to generate all the products. Fundamentally, for the product, KD, we call it, I think Kurt has covered this today, KD we call it AOP, parent optical property. When it's a parent optical property, what does it mean? It also depends on the light field. For the same water body, light, the sun is overhead versus light at the horizon, the KD 490 is very different, can differ by 30, 40%. Okay, same water. But this ratio, pretty much the same. For the light, for the sun at overhead, or for the sun at near horizon. So this ratio is almost independent of sun angle, but this is a AOP dependent psi angle. So these two actually, the optical properties do not match. So these are the fundamental caveats or issues with this kind of simple ratio derived optical properties. Okay, so that's some of the kind of in concepts. In practice, as shown in many presentations or papers, the ratio derived KD really doesn't work well, especially in coastal waters. Here is a publication by Derek and Stramsky. You can see this measure KD, this is algorithm derived KD by the ratios. For the higher value, you can see significantly underestimated, as shown here. This is a log, I think. This is log, means this is 1 to 1. Then, but no, this is simply the difference. So this is a perfect match, but for the higher values, significantly underestimated by nearly, here is 100%, so that's about 50, 60%, significantly underestimated by these simple ratios. So, as I said, we have IOPs. Then from IOPs, we can do this more analytically or scientifically instead of using statistics to do simple ratios by regressions. So radiative transfer, KD is actually a function of A and BB. Okay? I don't have time to do the derivations. If you are interested, you can read the papers. KD is a function of A and BB. M0 and V are just two model parameters. And when you know and BB, you can model this. And M0 is a function of psi angle. So you put in psi angle, you put in A and BB, you can calculate KD for given situations. And I just told that A and BB can be quasi-analytically derived from RS. So when we know RS, we can know A and BB. Give me a psi angle, then we can get a KD. Straightforward from radial transfer without any sort of kind of regression, sort of kind of analysis or regression development. And for this system, there's no deviation case 1, case 2. It's radial transfer works the same for case 1 water, case 2 waters. There's no case 2 radial transfer, okay? It's one radial transfer for all waters. So this can work for basically for all waters.
Yeah, I understand that. So the idea is to set a model that relates IOPs and not AOPs with AOPs. But is there any reason to get that functional form, or is it just that it works? I mean.
Okay, the question is any physics for this kind of function form? Okay, as I said, you go to the radial transfer, this can be derived from radial transfer. Okay. This is all built into radiative transfer. But here, this part is really based on numerical simulations. This part is completed from radiative transfer. So that has basically, it's a physics. It's a physics-based relationship. Okay. So here's some examples. Here's measure KD 490. This is derived KD 490 from remote sensing reflectance for different waters, which has from oceanic waters right all the way to turbid Baltic waters. As you can see, at 490, it matches each other very well. And this line, this solid line, it's not a regression line. That's a 1-to-1 line. Basically, this is a evaluation how this system works, not a regression. Okay. So here's another way to look at it. The ratio derived 490 to the measure 490. You can see for this wide range of waters, most of them are within 25% without any tuning to some data sets. That's one way. We can also do the spectrum. If you have the spectrum of RS, you can get spectral A and BB. After you know spectral A and BB, then you can get spectral KD, spectral KD. These are two examples. So, but those are simple ratio regressions. That means for each wavelength, you have to do a regression. But here, when it's multispectral, hyperspectral, how you do those kind of regressions, right? So here with these IOPs, analytically, we call it semi-analytic derived from RS, then put into radio transfer, we can get a spectral KD for different waters. So that's one part about one example of applications of these IOPs. Again, why we want to know KD? Because KD is important to propagate surface light to deeper depths. We can get light at the surface, but how we get light at 5 meters, 10 meters, or 50 meters? You have to know the KD, is spectral KD. So that's why we all want to know how to remotely estimate the KD spectrum. Okay, people say, yeah, I don't want to use KD, I use PAR. Do you guys know what PAR is? Basically, the integrated light, the spectrally integrated light. Integration is from 400 to 700 nanometer. That's called, the general term is photosynthetically available radiation, PAR, okay? I didn't write it there. So basically, it's integrated light. Then become one, we can call it one broadband. One band just basically represents the visible band. Then for the visible band, it also normally expressed as a PAR Z at depth. The PAR at 0 is the E2 minus K PAR Z. Since we just use one number, then we can propagate surface PAR to deeper depths. And that PAR has been historically used in the models for photosynthesis. And historically, this K PAR has been written as KW for Kc times chlorophyll plus Kx, other components. K water is kind of presumably is a constant for pure water. The contribution for pure water, for K PAR, basically for the, as I said, the attenuation of PAR from surface to deeper depths. But actually, this formula is wrong. Okay, it's really wrong. This is okay for the, I always say, it's for the darker age. It's not good for the 21st century, okay? We are 10 or 15 or 16 years in 21st century. Actually, this was pointed out in 1988 by Morel. This formula is wrong. The reason is, okay, PAR, this PAR, it's a spectrally integrated value, okay? Then you do this kind of spectral integration, then you do this log and ratio, this K water is no longer a constant with the change, with the increase of depth. Simple reason, this E0 lambda and this basically E0 EZ lambda, it's not spectrally the same. As I showed you yesterday, the light with the increase of depth, the quality changes. At the surface, it's kind of a white light. With the go deeper, the light is getting narrow band wavelengths, so getting more bluer and bluer for the open oceans. Bluer and bluer basically means this K water, basically this K PAR, will getting smaller and smaller. There's no such a thing of constant K water. As Morel said, K water Z is no longer constant as soon as compared for layer of thickness. It's a simple math problem, okay? Also, it's put out this Kc is also not a constant. There's no such a thing of a constant Kc times chlorophyll. But in the early days, because we all try to make life easier and lazier, so that has been used for many times, but it's not correct. Basically, as I mentioned, because PAR is an integrated radiation from 400 to 700, so this K PAR is a log of this divided by Z. Z is depth. So this K PAR actually is light quality weighted. Whereas light quality weighted because it's light quality changes from surface to deeper depths. If you guys ever dive, you know that. Deeper, you look up the deeper water, as I think I have shown here. This is surface light. It's more kind of like white light. But get deeper, so 25 meters, it's all narrowed, all the photons narrowed to this band, this range of wavelengths. So the light quality changes with depth. So that's why this K par Z is not a constant with the increase in depth. I'm assuming for the same water body, okay, homogeneous water body. For homogeneous water body with increased depth, the K par Z is not a constant. That's a simple optical phenomena, okay? Here is you can run hydrolyte simulations to check this. Hydrolyte simulation shows that, okay, this is a par Z to par zero. Okay, this depth, this is a ratio of par at deeper depths divided by surface. This is a K par Z, K par Z. You can see K par Z at the surface, roughly maybe a 0.16, but then at a deeper depth, about 0.05. That's a factor of 3 difference. So K par Z can change significantly with the increase of depth, simply because the narrowing of the spectral range. It's easy to understand. All the photons, because the higher absorption by water, all the red photons are lost in the surface layer. At deeper depths, it's those photons have less attenuation, like the blue wavelengths can go deeper. So deeper light is associated with smaller attenuation coefficient. Yeah, I guess it's too much for you guys today, but I hope you just capture this, okay, general concept. K par Z is not a constant vertically. It changes with depth. So to represent that, here's a model. K par Z as 2 constants, K1 and K2 are constants, and then change with Z. So basically make this K par Z will smaller and smaller with the increased depth. Then we can use this to calculate the so-called euphotic zone depth. Do you heard that term, euphotic zone? Basically, we have a practical definition. When par Z at some depths, it's 1% of par zero, we call that depth as a euphotic zone depth, ZEU. And this ZEU times K par ZU equal 4.6, that makes this ratio be 1%. It's a simple math, okay? So basically, then we can use the K par Z relationship to calculate this euphotic zone depth. That's shown. That's basically here. This is 1%. This depth, this is about 70 meter, 75 meter. It's for this case, it's a euphotic zone depth for this case. And the euphotic zone depth, it's a very good representation of remote sensor reflectance. Remote sensor reflectance actually is a measure of the upper layer, okay, not simply the surface. It's a measure of the upper layer, the light of the upper layer. This upper layer depends on different waters. Some of them maybe just 5 meters. Some of them could be 30, 40 meters. Euphotic zone depth is also a measure of the upper layer. So these two have some kind of good representations to each other or matching each other. Historically, euphotic depth can be estimated using the Crowfield values, basically the Crowfield approach. Using Crowfield, put this regression number, so you can get an estimation of the euphotic zone depth. Now with IOPs, we can do the same, but more of an analytical solution instead of regressions. From remote sensor reflectance, we can get A and BB. From A and BB, we can calculate how K par changes with depth, right? Remember we said when K par at the depth is ZEU, then K par ZEU times ZEU will be 4.6. So put this into this math equations, we can solve ZEU for given A and BB and for given some angles. This K par Z is also a some angle dependent. Here is the validation, okay? This is measured ZEU. This is RS divided ZEU for a bunch of locations. For a range about 4 or 5 meters all the way to 80 meters, they match each other very well. Again, this line is not a regression line. It's a validation line. It's a one-to-one line. When you read the literature, you can see many times you will see regression lines. But here we are talking about validation line. When it's good, perfect, it's always on this 1-to-1 line. But in remote sensing, if you see some results exactly on the 1-to-1 line, automatically question it, okay? Because we have so many uncontrollable variables, how can you make it 1-to-1? Practically, it's impossible. So if someone show you, I get 1-to-1, 100% right, don't believe it. Something is wrong. Anyway, this shows that, okay, from IOPs, we can also calculate the Euphotic Zone depth analytically and match the measurements very well. So here is a global product from models. You can see this is a South Pacific gyre. It's all the way up to about 170 meters. That's what I think they measured 2004 for the Bioscope that cruise. So it really matched reality from sighted estimations versus in situ measurements. As I mentioned at the beginning, one of the key objectives for ocean color remote sensing is get primary production. So can we do that with IOPs? As I said, historically it's all using chlorophyll. Now we just say ignore chlorophyll. Then can we do the same thing, or can we do better? What is photosynthesis or primary production? Basically, this is the light. This is the absorption of phytoplankton pigments. This shows absorbed photons by phytoplankton. This is so-called quantum yield of photosynthesis. Basically says, okay, if this phytoplankton have 100 photons, absorbed 100 photons, how many of those will be converted to chemical energy? Roughly this about maybe 8% maximum generally. But this depends on the physiology of phytoplankton. It's a number, okay? But from photosynthesis point of view, what this is, this really shows photosynthesis. This is photo, this is synthesis. Conversion of absorbed photons by phytoplankton. So from ocean color remote sensing, we can do the same without chlorophyll to estimate primary production. Ocean color, as I said, the remote sensing reflectance, we can get a KD, no KD, then we can get the E at depth, right? Get APH, put it here. This phi will be from laboratory measurements or in situ measurements. So we can convert all of these things into primary production. For the details, you need to read a few papers. I will show you some results. Okay. For the phi, there are also models. This is basically this K phi is a constant. This phi m is the maximum photosynthesis or maximum quantum yield. So knowing this, E0 is here, and knowing this, so we can estimate this phi for different depths, for different, basically at different, the quantum yield at different depths. So put this and this together, we can get an estimation of primary production without touching chlorophyll A concentration. I just don't like chlorophyll. You see that already, I guess. Here are some validations, okay? The measurements at two sites. One is the Northern Atlantic, one is Southern Atlantic. For the Northern Atlantic, these green dots are using APH, estimated primary production. This blue is from ratio derived chlorophyll, estimated primary production. Here, again, the green is from using APH based IOPs, estimated primary production. These two are using the ratio derived chlorophyll to estimate primary production for the two basically measurements. As you can see, for both cases, actually using APH, doing a better job than using ratio derived chlorophyll. Why? I talked that already. The ratio of remote sensing reflectance at two bands really, it do not give chlorophyll. It's not chlorophyll. This ratio, okay, it's basically it's a ratio, practically it's a ratio A550 divided by A440. If you put that to BB over A plus BB relationship there, A550 divided by A440 It includes ADG 550, APH 550 times chlorophyll. The ADG for A440 include A water 440, ADG 440, and APH 440 times chlorophyll. This is so-called chlorophyll specific absorption coefficient, right? And here's the chlorophyll concentration. But in this ratio, at least we need to know this and this before we can get chlorophyll. But this guy and this guy, they are variables. They are not constants. And they do not always covariate with chlorophyll. If they really covariate chlorophyll, bingo, it's just one variable. So this ratio can get a chlorophyll. But these two, as I have shown a lot yesterday and today, they are independent variables. So because these are independent variables, how can we use one ratio to get a good estimation of chlorophyll? Cannot. So that's why from this ratio we get something. We call it chlorophyll. When that chlorophyll is put into the chlorophyll-based primary production model, guaranteed it will introduce big uncertainties. And that's why using the APH-based approach, in theory at least, we can get better results for primary production estimation. So here's some basically emphasize change of RS ratio not necessarily represents a change of chlorophyll. It could be simply a change of this or change of this.
Can you return to the quantum yield, the phi? Like, what does it mean? It means the number of photons. It's a specific value, or is it? Why is it depending on 1 over? I mean, why is E0 dividing?
Yes, there are. I don't think we have time to talk details, but generally, okay, that's the question is why this quantum yield decreases with increasing light. In one sentence, is kind of like sunburn. Okay, we have too much sun. Actually, it's not getting higher primary production. Actually, it hurts primary production. Okay. It's a photoinhibition, it's called. It's kind of like, I use the term like sunburn. When we have too much sun, we'll be burned. So we have to put a sunblock there. But in fact, they don't know how to put a sunblock yet, so they get a lower photosynthesis. That's a simple explanation. Okay.
Okay.
Mm-hmm. So basically it says, okay, simple ratio cannot give us a good estimation of chlorophyll. Then put that chlorophyll into the primary production models, it will generate more uncertainties. This is about the ratio divided chlorophyll, as you can see, for different regions, basins, actually they are kind of systematic, either overestimation or underestimation, because of different basins, the relative sedum is different. So that sedum information is kind of converted or interpreted as chlorophyll. So this is kind of basin sort of kind of analyzed. Fundamentally, as I mentioned a lot, ratio divided chlorophyll actually is total absorption coefficient. As you can see, they have a very good correlation coefficient because ratio, as I showed there, ratio of RS is a ratio of A. And A550 is almost constant, then that ratio basically gives us the total absorption at 440. And total absorption not necessarily represent chlorophyll concentration. Okay, that's enough about the chlorophyll. But if we really want to do a chlorophyll, okay, do a good job on chlorophyll, we really need to, get the chlorophyll specific absorption coefficient. See, we can get APH, right? From APH to chlorophyll, we need to know that APH star, the so-called chlorophyll normalized absorption coefficient. The way to do that, we need lots of information. In particular, we need to know the nutrient. Nutrient is a big contributor or impact or factor to affect the APH star. So one practice, that's about 15, 16 years ago, it's Carter. Try to use the temperature and nutrient, trying to get some kind of estimation of the APH star. So to really get a chlorophyll, as we did, we need to remove the sedum. Also, we need to have a good handle of the APH star, the chlorophyll specific absorption coefficient. Another thing about the traditional chlorophyll-based primary production model, it also needs a parameter called a PB or PB max, the photosynthesis parameter. This PB is actually that phi, that quantum yield times the APH star. That's what this is, PBM. As you can see, for different chlorophyll, this PB here, okay, has wide range of variabilities. This wide range of variability also is come from that APH star, the phytoplankton specific absorption coefficient or chlorophyll specific absorption coefficient. When a PB has such kind of wide variation, then the estimated primary production, you can imagine, has big uncertainties. So, in short, okay, to estimate to have a good estimation of primary production from remote sensing, the best approach is trying to avoid this APH star, because APH star is so hard, or actually at this point, it's almost impossible to have a good handle remotely. We just don't know how to really have a good estimation of this APH star simply from water color or temperature. Maybe in the future you have a laser, we have a different source which may have better information, but at this point we call this from passive remote sensing. We just don't have good handle on this. If we don't have a good handle on this, let's better avoid it. Okay, that's about the traditional sort of kind of chlorophyll-based primary production estimation. And I just introduced we can use APH, basically use IOPs to do a better estimation of primary production. Here's another example, okay, the so-called carbon-based estimation for production. This is growth rate. Growth rate is so-called chlorophyll divided by C, and this is light. Actually, this chlorophyll from GSM model. As I say, this chlorophyll actually is APH from GSM. This C is estimate from BBP. So now you see this growth rate is actually estimated from IOPs. Growth rate is IOPs, and this is from APH, so this net primary production is also actually from APH, from IOPs. So that's another example showing that using these IOPs, we can do a better job on estimation of net primary production. Okay, those are the kind of historical heritage sort of kind of application of IOPs. Now I'm going to show a few other examples of application of IOPs. Have you guys played this? Yes. This is the best optical instrument, right? And the cheapest optical instrument, $10, you can get a sensor, quote unquote. This is really the most direct and representative measure of water clarity, very intuitive. So basically, can you see your toe? You can see your toe, it's good water, right? You cannot see your toe when you step in water. That water must be really bad. So water, this Secchi depth is really a good intuitive measure of water clarity, especially optical properties. In particular, I like it is if your neighbor is doing, basically your neighborhood or your people doing business or doing other things, know nothing about the ocean or know nothing about ocean optics, they ask you, what do you do? Then how you explain to him? APH 440, that will take years to explain what APH 440 is. But it tells them, yeah, I want to tell you if that water, if you go there to play in summertime, I want to tell you if that water is clear or not clear, to see your toe. Ah, okay, I can quickly get it. Right? That's one of the products I really like, the Secchi depth. There are many ways to estimate Secchi depth. If you check literature, there must be hundreds of publications already to estimate respect to remotely estimate Secchi depth. Most of them is empirical. Here's one of them, as shown here. This is, okay, a regression. Basically, this is a Secchi depth, this is another Secchi depth. They use Secchi depth converted. Most of them are empiricals. Basically, as I say, empiricals, you just go there to take data, then do regressions. Bingo, you have it. But then you have a difficulty to explain why. Why it's like this? So in addition to empiricals, there are actually also theories. In the past 4 or 5 decades, actually 6 decades, it's this formula has been used to represent or explain the Secchi depths. This is a constant. We already talked about KD. We also talk about C, the beam attenuation. Okay, so and this C is so-called contrast. This is a reflectance of the disk, reflectance of water. So the difference divided by water, so-called inherent contrast. And again, this number gamma we call normally we use 5.5. So for this formula to work, we need estimation of C. And actually, C is much, much bigger than KD because C is a beam attenuation. It's A plus B. KD is A plus BB. And we have talked B is 50 times greater than BB, right? So C is significantly greater than KD. So that means this ZSD, it's really primarily determined by beam attenuation. Historically, because I have mentioned that remote sensing reflectance is a BB dependence. So remote sensing has no B there. So this cannot work from remote sensing because we cannot use remote sensing to get a B. Then many, many years ago, no people trying to use this except about 2011, Doran, the French group, tried to use this formula to get an estimation of Secchi depths. But the results is not that encouraging. Get a bunch of us wondering why using a theoretical-based formula didn't get a good result compared to empirical ratios. Yeah, they did get us to scratch our heads for some days. The nature found that actually that formula is wrong for Secchi depths. The reason is this is a Secchi disk. These are eyeballs. Our eyeballs have very, very fine spatial resolution. I'm old now. You can, I guess, even to the final raw, you can still see my white hair. What does that mean? That means our eyes have very, very high spatial resolution. How high that is? In 1 meter, we can differentiate a 0.2 millimeter of object. That's how high that spatial resolution is. What that means? That means, okay, this Secchi disk normally is 30 centimeter. Then 30 centimeter, 1 meter away, that means it's almost 1,500 times our eye's resolution. It's a humongous object. You would think of our eye as a radiometer. So our eyes actually measure a small portion of the light come out from this disk. So that means this disk, it's not a point source, but a broad, kind of like this wall to our eyes or to a radiometer. It's a broad source. But there's a historical formula. This formula treats the Secchi disk as a point, a single point. But actually, Secchi disk, it's a broad source target to our eyes. So that's why that formula, that theoretic formula, isn't really correct. So we come up with a new formula for Secchi depths. This Secchi depths, this KD, but this KD is not a KD of the broadband. It's a KD as a transparent window. What does that mean? When you put a Secchi disk in water, we are not using the broadband to look at Secchi. We're just using the most transparent window of water to locate if that disk is still there. We are not using the red band, because red band, those information gone far earlier. For coastal water, we are not using the blue band either. Blue band, due to the sediment absorption, those information all gone far earlier. But for coastal waters, we're using the 550 wavelengths. We can still see it. Because what we want, we just Yeah, I still see it, right? That's the whole answer. It's a yes or no answer. I'm not saying it's still a circle or some kind of distorted shape. That's not the answer. Our only answer is, do I see it or not? So do I see it or not really depends on that diffuse light coming back to our eyes. So that this about. The Secchi depth is the attenuation at the transparent window. So this is a new formula. How good is this? Again, we have to evaluate. Fortunately, we found about 300 points. Here is oceanic water, coast water, lake water, and a bunch of coast water. We put that together, and here's what we get. From remote sensing reflectance, we can get A and BB. I just showed we can calculate KD from A and BB. Okay, the transparent window basically means the minimum KD within the visible domain. Okay, so that's the transparent window, so minimum KD. Then here's the measured Secchi depth, this estimated Secchi depth. This is how it works. Again, this black line is, now this time this is a regression line showing the comparison between these two. Okay. On average, the two independent determination is about 18% uncertainty. 18% without any regressions or tuning. 18%, what does it mean? That means, I don't know if you guys ever test that. Our human beings, because Secchi measurement is subjective, so what you read maybe 9 meters, I can read maybe at 10 meters. That's common. So we have about 10% uncertainty for this. So a comparison between the two, it's only about 18% uncertainty. That means the formula itself just generates about 10% uncertainty. That's how good it is. So that gives us a validation of the new formula about the Secchi depth. So with that, with modest measurements, now we can generate a global map of Secchi depth, water clarity. Then you can tell your neighbor, okay, some of days, if you want to go to here to swim, you can tell them, yeah, it's clear enough, or maybe some days not that clear, so better pick another day. So here, roughly, is about 65, 70 meters for Secchi depth. That's deep, really deep. Okay, that's about the Secchi depth measurement. I know it's really kind of a more of a generalized kind of talk. So we are lacking details, but I'm trying to just expose you the applications, the possible applications of the IOPs. Here's another application of IOPs: water mass classification. For the various waters, we all want to kind of group them into different classes. There are many ways to do it. Here's one way, okay? For this area, okay, some of them may be dominated by sediment absorption. Some of them may be dominated by, say, phytoplankton absorption. Some of them may be dominated by, say, suspended sediments. How you know? With IOPs, then it's straightforward. You just use this kind of Turner sort of kind of a graph. You just scale them or classify them. So this part, this green, will be those waters kind of dominated by phytoplankton. Then this part, it's dominated by, yeah, here, it's by kind of sediment dominated waters. Then the turbulent waters here is out of the Mississippi. This is Mississippi River plume. So those are this part, dominated by suspended sediments, organic sediments. This pink in between basically shows the mixed waters. So you can use these IOP products to quickly map the different water classes, and if you have a time series of these, you can easily see the change from day 1 to day 2, how these water masses varies in a different environment. HAB. I guess you must know this term already, HAB, harmful algal blooms. This is a big term and a big subject. Anyone will come from Florida? Maybe not. Just the past week, 2 weeks, Lake Okeechobee have really big issues of these harmful algal blooms. It's really bad smells, to that bad. We can use IOPs to do a classification if that water has harmful algal blooms. Here's one approach. Basically using APH 6, here's a typo, should be 675, okay? Using APH 675, we can convert that to chlorophyll, or without conversion, it's also fine. APH 675, then compared with BBP 550, generally, it should go like this, has a trend, okay? But if for those bloom waters generally, because those are harmful algal blooms, those can grow quite big. Those big particles, then the BB 550 per chlorophyll or per APH 675 will be smaller. So when these are kind of under this regulation line of normal waters, then we can identify them as harmful algal blooms. The reason is when that thing is harmful, the zooplankton are smart, they will not touch it. So they will let them grow, so grow larger and larger. When it's larger, the phytoplankton, its per chlorophyll backscattering will be smaller. So that's one way to use IOPs to identify harmful algal bloom waters. Another way to, sorry, okay.
What if you have a small harmful algae growing?
Small, but this is...
No, these are big, but if you have a small one, how do you detect it? If you have
See, that's not bloom yet. So we can only do when it's a bloom. If it's not a bloom, this may not work.
No, the small cell.
Small cell?
Yes. So the small cell will still scatter a lot of light, even if it has a lot of chlorophyll. So this ratio might be closer to the...
I don't know. So, okay, let me repeat the question. The question is, for small cell blooms, can we still use this approach to identify harmful algal blooms? I don't have a direct answer to you, but that's a good subject to study, to analyze, to basically to research. Okay, that's for you now. I cannot get all the answers. Then that means there are no jobs for you now. Here's another way to do this, okay, for IOPs. From remote sensor reflectance, as I showed, we can get APH spectral shape. From APH spectral shape, here's a validation. Here, remote sensor reflectance, okay? The solid curve is pi, the measured APH spectrum. Open symbol is APH derived from this remote sensor reflectance. From this APH spectrum, normally people can do second or fourth derivatives. Use derivatives to basically enhance these wiggles. These wiggles represent pigments. Okay, represent contribution pigments. So people have tried to use either second derivative or fourth derivatives. Here's the fourth derivative. Basically, after you get the APH shape spectrum, then you do fourth derivative. Use that fourth derivative to relate to cell counts. This is K brevis, okay? Use that, then get a kind of a similarity index compared to that kind of pure samples. Okay, pure sample of that fourth derivatives versus this derived fourth derivatives. Get a similarity index. And here's a log scale of this K brevis. As you can see, there are quite good correlations between these APH curvature and the cell size or cell concentrations. Sorry, I should use cell density. So cell density is related to this similarity index of this APH shape. So from hyperspectral remote sensor, you can get APH shape, right? From APH shape, you do a second derivative or fourth derivative, compare that with the pure K brevis absorption, then you link that with the log of the cell density. That's another way to use to identify if this density is too high to this range, you can call that it's a bloom water. The bloom water with K brevis. That's another example using IOPs to do this. Bloom dynamics, also using APH. Okay, here is a study. I think this Philippines. Yeah, this is Philippines. This is Taiwan, I think. This is the so-called Luzhong Strait. It's common every year. I think it's in wintertime. There will be a bloom of phytoplankton. In the past many years, they use ratio derived chlorophyll. But that fails sometimes due to, as I said, the ratio do not really give chlorophyll. Ratio could be a CDOM, could be contaminated by CDOM. So here, in this study, that CDOM information will dish out, will excluded. It's pure phytoplankton information. So this shows the patch of high phytoplankton. Here is another patch near coast of phytoplankton dominated waters. Then using this, then we can see the time series. Winter time, then it's kind of start to bloom in November, highest bloom in December, then dying down in January, then kind of pass over to January to February, March. So you can use the phytoplankton absorption as an indication as an index to study the dynamics of this phytoplankton, kind of their in different environment, how they change from time to time, instead of using ratio-derived quote-unquote chlorophyll. Physiology, we want to see the quantum yield of fluorescence. That's the so-called fluorescence line height from satellite. If you, I think in the coming days or weeks, you will learn more about the satellite products. One of the satellite products is called fluorescence line height. From fluorescence line height, you can get this fluorescence, quantum yield fluorescence. And this part basically is APH. This is light, absorbed light, fluorescence, quantum yield fluorescence, transferred to the fluorescence line height. And this phi of quantum yield is related to the physiology, nutrients, iron limitation, all those things. So this is demonstrated by Bernfeld et al. In a global scale, how you can use these IOPs to infer if that is iron limited or not iron limited, or those things. Here's another very common you can see in the literature application of IOPs. It's get coastal water salinity. Maybe you don't know, or you know that there's a satellite, Aquarius, get a global salinity, okay? But that one has a spatial resolution about 100 kilometers, not 100 meters, 100 kilometers. That means 1 pixel is 100 kilometers. How can you do coastal water salinity? Impossible, right? So, but because of the conservative mixing between salinity and CDOM, then we can use CDOM information and the salinity information to use the CDOM to figure out or estimate the coastal water salinity. This is coastal water salinity, fresh water to really getting kind of a salty water. This is a relationship. There are many studies, articles showing this. But the thing is, this relationship, it's not conservative. What that means, for different locations, different estuarine, you may have developed different relationships. The mixing has their own features. So if you are interested in Chesapeake Bay or interested in somewhere here, you may have to take some water samples, take some measurements to find their own relationships. But this, at least from ocean color, from IOPs, can push this estimation of salinity from really open ocean to the coastal regions. Salinity is very important for physical oceanography. Not getting into the kind of sinking or suspension or mixing in the upper water column. Here's another example showing the salinity, this Caribbean Sea. And you can see salinity and absorption at 300 nanometer. Where generally they have a good linear relationship because of the conservative mixing. PCO2, when we talk about carbon, this dynamics, the CO2 thing, we want to see where has a high, the partial pressure of PCO2, because that really determines the atmosphere CO2 getting into water or vice versa. So from satellite, as I said, satellite do not give us chlorophyll, give us IOPs. So this IOPs, you put a temperature, salinity, you can get an estimation of the PCO2. So these are examples. So if you have some interest, you have some measurements of PCO2 at different regions, you can do similar thing, trying to estimate PCO2 in a larger scale. So to summarize, okay, traditionally many applications are built around the chlorophyll. But actually now with the IOPs, we can do the same, or we can do better. Like the KD, KPAR, Euphotic Zone depths, Secchi depths, or those things. Okay, so this is, as long as you can do IOPs, as I can develop a good relationship between IOPs and the other properties, you can do a very good job for the applications. More importantly, when we develop an application centered on IOPs, then we no longer really need to specify, we call that concentration normalized optical properties, the so-called APH star or BB star or those things. Think of chlorophyll is a biological property. Absorption is optical property. To link these two, we have to do a ratio of the absorption to concentration. That's called this concentration normalized property. This concentration normalized property is never a constant. At a very spatially and very temporally. Without a good handle on this normalized property, we can never do a good job on estimation of the concentrations, especially chlorophyll. So when we have an application, if the application can be built using simply IOPs, then you bypass this difficult to handle optical property. Also, when we have used IOP as inputs, many products, as I mentioned, like the diffuser attenuation, Euphotic Zone depths, Secchi depths, primary production, which can be estimated much better, more accurate than use this ratio-derived chlorophyll. Okay, as there are a bunch of examples I've demonstrated. Also, as I said, it's really, the many applications could be developed, built, centered on IOPs. What's the slogan? Sky's the limit. It's the same thing. Sky's the limit. Just be creative. Think about the applications, especially when it's related to the environment. Okay. I guess I will stop here. And if you have any comments, questions, we can continue the discussion.
My question is centered on hyacinth. Is there any study done on the use of IOPs to study hyacinth?
Okay. Some kind of floating plants. Okay. For floating plants, so okay, here's a question. Can remote sensing detect or analyze these kind of floating plants? Is that a question?
Yeah, or can you use IOPs to do that?
Actually, for that purpose, maybe we can even do easier without IOPs. See, so far we have been, the remote sensing we have been talking yesterday, it's all the properties submerged or diluted in the water column. And we are not assuming anything floating. Okay, when it's floating, then it's a different domain. Then it's more kind of like terrestrial remote sensing. Think about as grass. When you have that kind of dense material floating on the surface, it's basically grass. It's grass, it's a terrestrial remote sensing. We can use the near infrared information to identify, to locate those floating materials. But if it's that specific material or floating algae, it depends on spectral characteristics. Like for instance, if you read news, this is the big event in the Caribbean, it's the sargassum. The sargassum is just floating everywhere, pretty much, and damaging the beach. But that has some kind of special spectral characteristic. We can try to say for this location has a dense floating sargassum. But that could be kind of mixed with other or misidentified with other floating algae. So really depends on that substance, that specific algae, what is spectral characteristics. That's the most important thing. So you need to take some field measurements to figure out, especially the key thing to figure out its remote sensing reflectance. Does that have a special, unique spectral characteristics? But generally, when it's a floating algae it's a different category to what we are talking yesterday today. We have been talking yesterday, it's materials diluted or suspended in the water column, not floating on the surface. Hope that answers your question.
Concerning your improvement of the Sekidis formula, I'm thinking, you remember that paper by Boyce who studied like with historical
Yes.
Sekidis? Yeah, would it impact his results, that difference in the...
Okay, here the question is, with the new Seki model, will that have impact to the, I think it's 2012 Boris century-old chlorophyll versus Seki depth relationship? No, that's a two different things. The answer is, that is basically, it's two in situ measurements. In situ measurement of chlorophyll, in situ measurement of Seki depth, they try to build an empirical relationship, then trace back to use the Seki depth, get an estimation of chlorophyll kind of 100 years ago. But here we are talking about is how Seki depth is related to optical properties. Then how we can improve the remote sensing of Seki depth using ocean color. But the good thing is, with that data set, then we can trace back even to estimate the Seki depth from CZCS. In the past, it's out of imagination. Now we can use the CZCS data to estimate Seki depth in the 1970s to 80s. Yes. John.
Can you do it the other way? Can you use Seki depths from hundreds of years ago to estimate the optical properties, or no, because there's 2 degrees of freedom?
No, exactly. See, Seki depths, no, we can get a KD. From Seki, we can get a KD, a transparent window. That's it. Those are two, sorry, I need to repeat the question. Can we use the Seki depths to estimate the light field many years ago or 100 years ago? But maybe not, because from Seki depths, we can get a KD at 1 wavelength. It's a transparent window. But we still need a BB term to get the remote sensor reflectance, basically to get a light field. So maybe not enough.
And also, you wouldn't know which wavelength the transparent window was in, would you?
No, we don't. We just know the Seki depths. But we can use the data now. If I know the depth, it's basically it's 10 meters. Roughly, you can estimate likely transparent window. That I can do. Actually, we already did using vias. Yeah, for different range of the depths of the Seki depths, roughly it's related to different transparent window. That can be done.
Sorry, does the model for the primary production has been applied globally and compared to other models of primary production? Because what I wonder which is the uncertainty of your quantum yield function.
Okay, here's the question is how the absorption-based primary production, when it's applied to a global ocean, how that compared with the historical chlorophyll-based primary production estimation, right?
Yeah.
Right.
Or with other models.
Or with other models. That's an ongoing study. The reason is, say for the historical chlorophyll-based models, they have the PB max will kind of figure out, okay, that photosynthesis parameter. For absorption-based approach, historically there's no measurement of absorption coefficients, phytoplankton absorption. So there's very limited study about the quantum yield, how that change globally. So now we are starting to build the data to try to understand how that phi, especially phi max, change globally. After we get that piece of information there, then we can do a global estimation of primary production.
And the estimation of phi is independent of the estimation of
APH, right. Those are two independent parameters. Yes.
Thank you.
Yeah. All right, thank you guys. I guess we are all waiting for the party time, right? Good, okay. Thank you all.